I told you earlier that we have 2 CppCon attendees that are actually in high school. I introduced you earlier to April, and now I've got up here Zoe Carver, who is a high school kid. He's tall enough to be out of high school, but he's still in high school, right? Hi, Zoe.
Hello.
You really do C++?
Yeah, well, I've made a few commits to libc++.
I think you must go to a different high school than I did. So, have you ever heard of our keynote speaker today?
Yeah, I was actually lucky enough to get to talk with Sean earlier this week. And ever since, I've been looking forward to this talk. I am absolutely certain that every single one of you will learn something after this talk. So, will you please help me welcome Sean to the stage?
Hey, good morning. So I'm going to apologize up front for drinking some water, but I've been talking all week and my voice is kind of shot. It's been pretty amazing at this conference and to see this conference grow over the years. Like 6 years ago, I gave this talk where my tagline was, "That's a rotate," and it wasn't intended to be something that would spread virally and not something that would last for 6 years. That is truly amazing. So I'm a senior principal scientist, a very, very high title, kind of embarrassing, working on the Photoshop team at Adobe. Most of what I do at Adobe is not actually graphics, but it's worrying about the architecture of the application. And that's somewhat what this topic is about, is the notion of relationships, right? Of how things interconnect. And this is a part of a series of talks that I've been giving that started 6 years ago with that C++ seasoning talk that I title now the Better Code series of talks. And all of my Better Code talks have a goal. So if you haven't heard my talks, I picked the word goal very carefully. These are not rules. These are not guidelines. I don't want code to not be, to be blocked from going in because you're like, hey, Sean said don't do this and you did this. Because these can be, in practice, very difficult things to achieve. And so all of my goals are non-prescriptive. I can tell you what not to do, but I can't tell you what to do. But what I can say is if you actually spot, this is the one rule, where if you actually spot a contradiction in a code review, don't let that code go into your project. Why? What's a contradiction? It's a bug. So the clickbait title for this talk would be How to Write Bug-Free Code. Okay. So I'm going to build on a quote here. I heard this quote years ago, and now I can't figure out where it came from, and this is my own paraphrasing of it. I thought it was from the movie Searching for Bobby Fischer, but the internet disagrees with me. So, a novice sees only the chessmen, an amateur sees the board, and a master sees the game. Right? So what do we mean by see here? What is it that the master chess player sees that the novice doesn't? And the answer is the master sees the relationships. Right? And this is a problem for us because computer scientists are bad at relationships. Now, I know my wife would agree with this statement. Many of you probably have partners who would agree with this statement. But what I mean by this statement is that computer scientists, we tend to talk a lot about types, and we tend to talk about algorithms. That might be partially my fault. But we don't talk about relationships. And there's this underlying fabric that knits those things together. Right? So in this game where we're talking about relationships, let's review what the pieces are. Right? A relation in math is a set of ordered pairs, mapping entities from a domain to a range. Right? It's distinct from a function in that the first entity doesn't uniquely identify the second entity. A relationship is the way two entities are connected. So that's what we're talking about. How are things connected? Now, relationships have properties. They have cardinality, which is the maximum number of times an entity can be related to another entity. And they have modality, which is the minimum number of times. Okay? The diagram in here is stolen from ER diagrams, entity relationship diagrams, from database theory, but I'm not going to be talking about database theory today. For any relationship, there's a corresponding predicate, a relationship that's implied by that relationship, right? If it's true, we say the relationship is satisfied or it holds. Right? John is married to Jane is a relationship. The corresponding predicate is John married to Jane? Right? Now, a constraint is a relationship which must be satisfied. What do we mean by must? Right? Anybody? A little circular here. For another relationship to be satisfied. Right? So, for example, the denominator must not be 0. That's a relationship. For the result of division to be defined. Okay? The notion of a constraint is strongly related to the relationship of implication, right? This is a very basic Boolean relationship. A implies B. This is the truth table for implication. The only time the truth table is false is if we have A and B is not true. Okay. So I'm going to introduce a very simple notation here for talking about relationships. This is the notation that I tend to scribble on my whiteboard a lot. It's incomplete. You can't represent everything in this notation. It's not intended to be formal, but it does help me convey the structure of software. So entities are represented with a rectangle and relationships with a circle. I use a circle instead of the database triangle because when you're writing on a whiteboard and you're writing sideways, your triangles start to look like rectangles. I'm sorry, not triangles, diamonds. So these things form bipartite graphs. What's a bipartite graph? It's a graph where you have two distinct different node types and one node type is between every other node type, right? So to connect an entity to another entity, you must do so through a relationship. You cannot connect a relationship directly to a relationship without an intervening entity. If you had a relationship connected to another relationship, that would be a composite relationship and just one relationship, right? So it would collapse, right? So this is a nice way to kind of look at the structure of things. Now, we can represent implication in this by adding directional edges to our graph. So this is shorthand for given entities B and C. A is any entity such that R holds, our relationship R holds, is satisfied. Right? So I read this as B and C implies A, right? And that doesn't mean implies a particular value. It means implies a particular set of values, potentially, that satisfy this relationship. This is not quite a function, although it could be if we only had one result. Okay. Relationships and objects, right? As soon as we have two entities, we have implicit relationships. And the memory space is an entity. What this means is as soon as I have one object in an entity, I have a whole bunch of relationships that go with that. When an object is copied or moved, any relationship that object was involved in is either maintained or it's severed. Maintained meaning the relationship still holds, and severed meaning it doesn't with respect to the destination object. So as an example, if I were to clone myself, okay, I am married to my wife. That relationship continues to hold. There are one of two possible options for my clone. My clone may be married to my wife, depending on what state we live in which case the relationship is maintained, right? If my clone is not married to my wife, then the relationship was severed. Those are the two possible outcomes. When an object is destructed, any relationship that object was involved in is severed. I can't have a relationship to a non-entity. Okay? I cannot maintain some relationship to nothing. This brings us to the notion of a witnessed relationship. So a witnessed relationship, I used to call these in a previous talk reified relationships, but some good computer scientists corrected me. A witness relationship is a relationship represented by an object, right? So we have a concrete object that's a token for some relationship. A wedding ring, which I'm not wearing mine, but a wedding ring would be a token for a relationship. As an object, a witness relationship is copyable and equality comparable, and we'll talk more about that in just a minute. But that can cause a bit of a problem. When an object, witness relationship or not, is copied or moved, any witness relationship that that object was involved in is either maintained, it's severed, or it's invalidated. What do we mean by invalidated? Right? What we mean is that that object lost its meaning, and we're going to talk more about that in a moment. Right? So when we say, oh, if you insert into a vector, then if you had another iterator into that vector, that iterator was invalidated. My iterator is a witness to the relationship, and doing that insert shifted the memory, and now that iterator is invalid. It's lost its meaning, right? Right? It didn't get severed, my iterator didn't get nulled, and it didn't move magically with the object that went away to maintain that. So now we have three states we're concerned with. Okay? And these states also apply to the witness relationship itself. It's an object involved in this relationship, right? So, when an object is destructed, any witness relationship that object was involved in is either severed or maintained, right? We still can't maintain a relationship to a non-entity, but now we've got this other thing to worry about, not just that our relationship is broken, but that it's invalidated. Because of this notion of losing meaning, sometimes we might choose not to implement copy or move for a witnessed relationship. Right? This is a conscious choice, right? When we say that unique pointers or mutexes or locks are not copyable, what we're actually saying is we're choosing not to copy them because of the ramifications that would follow if we did. Okay? And this whole idea of invalidation is how we get iterator invalidation at a distance. And that's kind of the scary quantum effect thing, right? I change an object over here, and somehow some object somewhere else in my application just got zapped. It magically lost its meaning, right? All the way across space and time. So let's talk a little bit more about meaning and the board in our game, right? Those are just the pieces. So what's the board? The board is structures. Right? A structure on a set, going back to math here, consists of additional entities. So I've got some set of entities, and I've got another set of entities that in some manner relate to the set, endowing the collection, that's our set, with meaning or significance. Okay? That's the definition. It's a little abstract. It's a little philosophical even. So step with me into the void. So this slide is void. What I mean by void is it's dimensionless. It has no width, it has no height. It's always existed. It's not in time. It's nothing. Into this void, we're going to drop 4 bits. Now, of course, since we have no time, these bits were always there. You guys just weren't paying attention. Okay. So now we ascribe meaning to those bits. What do those bits mean? Maybe those bits mean 4 bananas. Maybe those bits mean the color blue. Maybe they just mean the abstract 4, right? This is a representational relationship, and there is nothing in the machine that tells us what these 4 bits represent, only what we intend them to represent, okay? That's a representational relationship, and that's what ascribes meaning to our objects. Now, the collection of bits here as a whole, we refer to as a type. What is a type? It's a pattern that we can use to represent other things within the domain of our entity, right? So maybe this collection here could represent values in the range of -8 to 7, right? It's a little signed integer, a 4-bit signed integer. So we could then have another object of the same type. It was always here, you guys just weren't looking, in our void that also represents -8 to 7. Okay. And now that we have 2 objects, we can talk about the relationship between the objects. Even if the objects were different types, we would have a relationship which is, are they the same type? Okay. So now we've got a relationship where we can compare them and say, is 4 greater than 3? Trust me, you guys, if you're like, where is Sean going with this? There will be code. Okay. So we've got then this representation in terms of bits, which means we also have representations that aren't about the values themselves, but are just about the bits. So if our representation is unique, then we can hash that representation, and the hashes not being equal implies that the values that those 2 things represent are not equal, right? So now we've got a correspondence between the representation and functions that we can apply to the representation and the meaning of those operations. Okay. But objects don't exist in this void. They exist in a memory space, okay? And they exist in time, and they are physical entities that exist in the world. We talk about them being virtual, but they're really not. They're physical bits inside of your machine, right? So what makes our 2 objects here different than just some arbitrary set of bits that we have somewhere else in the address space? The only difference is the meaning we ascribe to those bits, right? As soon as we have an object in the memory space, now we have additional relationships. Our object has an address, okay? The other object has an address, and we can compare the addresses, right? This is true of every physical object. Every one of you guys has a coordinate within the universe, okay? And every one of you guys is in a relationship with everybody else in the room, right? We can compare your coordinates, okay? So these are called physical relationships, right? So don't go home and tell your spouses, hey, I was in a physical relationship, right? Or your partners, I was in a physical relationship with everybody at CppCon. Okay? Now, because these things have coordinates, it means that we can do things like sorting them, okay? We're putting the values in memory now implies implies a corresponding relationship to, the location in memory implies a corresponding relationship to the values. The smaller value is before the bigger value. Okay? That's what it means to sort data, a very useful operation. We can also use these objects with an operation such as plus. We can add them together to ascribe new meaning to other bits in the machine. So we add 3 and 4 and we get 7, okay? And what we're saying is this is not just 7, this is the sum of those 2 other objects. That's what it represents, right? So we're taking the meaning of the initial objects and we're creating new objects with new meaning. So let's talk a little bit about safety. An object instance without meaning is invalid, okay? So I can have bits in the machine which are an object but somehow have lost their meaning, such as an invalid iterator, which we talked about before. An object in an invalid state must either be restored to a valid state or be destroyed, right? We somehow have to get the meaning back into that object, or we have to let that thing go. If we just let it wander around the system, it's spreading nonsense throughout our machine and our program becomes invalid. So we want to localize the damage, right? We want to make sure that we're conscious that it's there and that the damage of these invalid objects is contained. This relates to the idea, if you're familiar with Alex Stepanov's book, Elements of Programming, to the idea of a partially formed object. A partially formed object in Elements of Programming is an object where the requirements are only that you can assign to it or destruct it, right? I can either put meaning back into the object or I can destroy it. Those are the only two operations that are allowed. Now, it's a little bit weaker to say about an invalid object. If you think about a doubly linked list, if I'm inside the class for a doubly linked list and I'm doing some operation, at some point I'm going to need to change one of the links in my list. At that point where I've only changed one and I haven't done the corresponding change for the backlink, my doubly linked list is now in an invalid state. It doesn't, at that moment in time, represent my canonical list. It's not completely devoid of information, but it has in some sense lost its meaning. And so I need to come along and do another operation to restore the meaning. So an operation which leaves an object in an invalid state we refer to as being unsafe. Okay? So an operation that can nuke some other object in your device is an unsafe operation. Now, unsafe doesn't mean bad. It doesn't mean you should never call it. In fact, we can prove that there's a relationship between safety and efficiency, and you cannot have complete efficiency and complete safety both, provably. std_move is an unsafe operation. And I want to bring this up because the standard wording, although it's improved in the latest standard, I still somewhat object to the standard wording on this. The post condition, the required post condition of std_move is that the object that was moved from is in a valid but unspecified state. Okay? Well, what do we mean by valid and unspecified? If it's unspecified, it has no meaning. Okay? The standard itself kind of contradicts itself. It talks about iterators being invalid, right? And it talks about objects being valid after a move. Okay? And when they say an iterator is invalid, it means you have to assign a new iterator into it or you have to let it go, but you can't dereference it. Well, you also can't dereference an iterator to an end. You can't dereference an iterator to the beginning. So kind of structurally, there's no difference in that. Really what invalidation means there is that the meaning of that object is lost. So, and I want to be clear because I said that at a prior talk, that std_move is unsafe, and that turned into this whole big debate because it followed some stuff that Eric Niebler said, that Sean Parent said std is safe, that std_move is bad. Sean said std_move is destructive. No, I said something very precise and very particular, right? So it's not bad, it's just unsafe. Now, in C++20, we have two new features specifically about relationships. Can somebody name them? I heard concepts. It's number one. What's the other one? Ready? Contracts. Okay, I lied. In C++20, we have one new feature specifically about relationships. Concepts. So concepts, the term was originally coined in this paper, Fundamentals of Generic Programming. This is from James Dennert and Alexander Stepanov. And this is what they said. we call the set of axioms satisfied by a data type and a set of operations on it a concept. This work is very tightly related to this paper here, an axiomatic basis for computer programming. This is from Tony Hoare, Sir Tony Hoare. This was published back in 1969. And this introduced what's known as Hoare logic. It's also known as Floyd Hoare logic. Bob Floyd was Tony's advisor. I'm not going to go into Hoare logic, but you'll see the relevance here in a moment. So let's talk a little bit about concepts, right? Two objects are equal if and only if, right? If with two Fs, their values correspond to the same entity, right? So we have two objects, they have some meaning, they represent 4, some abstract 4. Those two objects are equal only if they represent the same 4. There's only one Platonic 4, right? One truth for that. From that, we define the following properties, right? It's not going the other way around. People think the axioms for equality are what define equality. No, it's the meaning of equality that defines equality. The axioms are the minimum set of relationships that we can derive from that definition as to what to represent equality. And these, in fact, define any equivalence relationship, not just equality. So with concepts, axioms follow from our definition. A collection of connected axioms form an algebraic structure, right? That's what algebraic structures are in mathematics, connected axioms. Connected type requirements form a concept, right? So we're lifting a mathematical idea of algebraic structures into the computer science realm. So what do I mean by connected? Well, operations like copy are connected to equality. In fact, equality is our most basic operation because it tells us whether or not two things mean the same thing. And so every other thing that we do, we define in some way in terms of equality. That's known as equational reasoning, right? So copies are equal and copies are disjoint. Right? And we can extend this to other operations. A natural total order is a total order that respects the other fundamental operations on a type. Right? A total order has the following properties. It obeys the trichotomy law, and it's transitive. Right? So here we can say natural total order, right? For all n, which are within the integer domain, n is less than n plus 1. Right? Why don't we have a natural total order and define operator equal on complex types? There are many total orders that we could define on complex types, but there are no total orders that are consistent with the other operations on a complex type. So we omit defining operator equal. Operator equal should mean the natural total order. Now these quantified axioms, for all there exists, those are quantified axioms, are not generally actionable, right? I can't write code and say that require for every possible thing pairs of values that I could call this function with, this is satisfied. I don't have a way to describe that. People continue to try. What you need is an algebraic system layered on top so that you can prove and reason about these quantified axioms. In fact, Alex Stepanoff and Dave Masser, when they created generic programming, went off and created an entire programming language called Tecton, which is all about formal proving of software and algorithms. And in fact, not many people know this, but all of the STL has been formally proven, or circa, the HP STL, has been formally proven using Tecton. So concepts in C++ work by associating the semantics, these meanings, with some name, right? Which is exactly what we do when we're talking, right? What do the words coming out of my mouth mean? we have some set of associated semantics. So we lift that same idea into our software, and we associate meaning with our named operations. So software is defined very fundamentally on algebraic structures. This is how it comes together. Now I want to talk a little bit here about contracts, right? Even though they didn't fall into the even though they didn't land in C++20, contracts came out of this paper. This is a slightly newer rendition. I couldn't find an original copy, but it was originally published in '86 by Bertrand Meyer. That's a picture of Bertrand. So it's applying design by contract, okay? And it came out of, his work came out of exactly the same work as generic programming, right? This work by Tony Hoare, An Axiomatic Basis for Computer Programming. They share the same roots. Contracts were originally part of the Eiffel programming language. And contracts allowed the specification of constraints. We had pre- and post conditions on functions, and we have class invariants. What does it mean to have a class invariant? Right? What we mean is a class invariant is a constraint, a set of properties that must hold when the value is valid, when it has meaning. Okay? That gets a little tough. The normal way that we represent this is we're allowed to violate the class invariance when we're inside of a private method, but we can't when we're outside. Except for efficiency, we need unsafe operations outside. Okay? So class invariants get a little tricky. So contracts are actionable predicates on values. Bertrand ran into exactly the same issue that Alex and Dave ran into. This is a quote from Bertrand's paper. In some cases, one might want to use quantified expressions of the form for all x of type t, px holds, or there exists x of type t such that px holds, where p is a certain Boolean property. Such expressions are not available in Eiffel. They just can't be. Right? So concepts describe relationships between operations on a type, and contracts describe relationships between values. And the distinction is not always clear. Right? If you think about it, the requirements for the comparison operation past std sort is that the comparison must implement a strict weak ordering relation over the values that are being sorted. Is that a contract? Is that a property of the type? Okay. Or is that a precondition on the function object that we're passing in? It's not always clear. And there's a bit of a difference in the way we handle contracts and the way we handle concepts. Concepts are used as a compile time constraint to select an appropriate operation. Okay, if a concept isn't satisfied, then we just ignore that function and we go look for a different function. And if there is no other function, then we get a compilation error. Contracts assert at runtime if an operation's preconditions are not met. Okay, so it's the equivalent of just writing assert in there. A runtime constraint to select an appropriate operation is known as pattern matching. Right? We don't have pattern matching in C++, although I've seen a couple papers proposing it. So let's take a look here. We could have a concept on a function like this. This is a little bit of pseudocode, our double requires clause here. People hate that. But what this is saying is that for whatever type I is, the expression not I less than 0 must be a valid expression. Okay. We could have a contract that says, for whatever value I holds, I cannot be negative. Okay? Or we assert. And in theory, we could have a pattern match that says, for whatever value I holds, I cannot be negative, and if it is, we go try to find another copy of F to execute at runtime. That's what pattern matching is. Right? So all of these ideas are very closely related. I want to talk briefly about one more important relationship, and this is the whole part relationship for composite objects. Right? The relationship for whole part relationships means that objects are connected, right? We can have a local part and a remote part. Here, C is our remote part. Non-circular. We can't just hold on to C itself and have it also connected to its parent. So we can't do that in a whole part relationship. A whole part relationship means things are logically disjoint, right? So I can't have some A prime and some A sharing some state. That's not allowed. And they're owning relationships, right? And what that means is that if I made a copy here and I destruct the object, the whole thing goes, right? Including the remote parts. So that's the whole part relationship. Standard containers are composite objects. Composite objects allow us to reason about a collection of objects as if they were a single entity, right? An entity in the relationship, in the structure of our application. That's why this is important. It simplifies our reasoning about a collection of objects down to that is just one entity, right? So this is why I give a talk on no incidental data structures. Right? I see this a lot. I've got a view class, and it's got a shared pointer to other views, and I could be hanging on to those views, and I've got a weak pointer to the parent, and I've got this whole tangled mess of objects. I can't reason about that. I don't have an entity. I have a whole bunch of complex relationships spread all over my code. So if I can get rid of that and turn it into a container, something like an Adobe forest of views, now I've just got one box I can draw on my whiteboard, okay? And I can think about that. I give another talk that has been cited more times than I can count at this conference on no raw loops. And I put up this piece of code. And this piece of code is a rotate. It's a find if followed by rotate, but we'll call it a rotate. Right? So that's a rotate. That's for Connor. Right? Why do I want that? That lets me take this big mess of code, I distill it down to a function, and that function now is just one relationship. I can see the structure. I can reason about the structure, about what's going on. I can draw it on my whiteboard. That's why no raw loops. So now we finally get to the game. The game is architecture. What is architecture? Architecture is the art and practice of designing and constructing structures, right? That's what architecture means. How many people have software architect in their title? Okay, a few. How many people knew that? Who are architects? Anybody? Right, that's what architecture means. When we're talking about software architecture, we are talking about taking these structures and designing them, putting them together purposefully, right? That's what we do. So let's give a concrete example here. I was given this task recently. This is the basic description of the task. Save the document every 5 minutes after the application has been idle for at least 5 seconds. That's the description in English. So how do I approach this problem? Well, the first thing I do is I say, well, there's this piece, save the document every 5 minutes. I know how to create a scheduled timer that will execute every 5 minutes, so I can ignore that piece. Now, as an exercise for you, I was absolutely wrong. I can't ignore that piece. If you realize why, after you've seen the rest of this, you'll also know how to fix it. So I'm not going to tell you how to fix that. Okay? That's an exercise. So, but in any case, I'm ignoring that for now. That leaves me with this, and I generalized it a little bit. After the application has been idle for at least n seconds, because somebody pulled 5 out of thin air, do something, because it really doesn't matter if we're saving or not, right? So we're going to generalize this just a little bit. And I wrote this piece of code. And what did I say? Well, I need to know when was the last time we were idle. So somewhere in the application that's going to have to be provided, so I'll just stick in a reference to a global variable, which is the last time the application was idle. Okay, and then I'm going to need some operation to schedule a task to execute at a particular time. Now I have that, it's been provided by the OS somewhere, so I'm just going to assume that it's outside of my domain, right? I know that I can go find that. It's somewhere in my application. So I need those two things. Now given those two things, I can write this function after idle. And what I'm going to do is I'm going to calculate when I should execute this task, right? So I'm going to take the current clock, subtract away the idle, minus the delay, which is going to be our 5 seconds, and that's going to tell me when to execute. And now I'm going to say, should it be executing now or not? If not, I will kind of do this funky little recursion here where I will say, schedule not a time to actually execute the task, but to check again, right? Why check again? Because my last idle is a global variable. It might get updated, okay? So what am I going to do? I'm going to say, oh, I should execute this task in 4 seconds. In 4 seconds, I check again and say, well, no, user did something, maybe 3 more seconds, okay? Until I finally execute. And the final execution is here. Now there's a couple problems with this code, right? My last idle probably wants to be atomic. I wanted to put it as an atomic on the slide here, but I can't because std atomic requires that the value be no except default constructible, but for some reason a time point is not no except default constructible, so the compiler gives me an error if I attempt to do that. But if I'm assuming that this is all getting scheduled through a run loop on just one thread, this still works fine. I've also got a bit of an issue here with registering my task, which is when I call this, my task may get scheduled and executed through my scheduler, or it may just execute immediately. And execution contexts matter, right? So it might be a little bit surprising and introduce weird bugs in my application if 99% of the time that thing gets scheduled and executed in some context, but every once in a while it gets executed right now and whatever code is surrounding this call wasn't ready for that. Okay. So a couple small issues. But let's ignore those and let's stand back and look at the structure of this function, right? We can draw it now. So what have we got? We've got last idle, we've got now, and we've got delay, and those are related to our when, okay? And then we take when in our task, and those are related to invoke after. And then invoke after is going to do some funky recursion thing, and we're just going to ignore that, because it's just this graph repeated over and over, so that's not interesting. Okay, so that's the structure. So what are the dependencies on this little function? We have more dependencies than we have going on inside the function, right? We've got last idle as a global variable. We've got now as some global function. We've got our delay operation, which is an argument coming in. We've got our task operation, which is our argument coming in. And we've got a dependency on this global operation to do the scheduling, okay? And it's very clear when we look at it this way that we have two things going on inside of this function, right? We've got everything over here on the left and everything over on the right, and they're very loosely connected, right? So let's just look at the first part of that. What is this relationship, right? Could somebody name this structure? What is this thing? It's not a rotate. Okay? This is what that is. It's a timer. It's like a kitchen timer. Okay? A kitchen timer, you can add time to it, right? And it ticks down. You can't speed it up without breaking it, okay? But you can add more time to it, right? So that's what that structure is. It's a kitchen timer. So let's take another stab at writing this function. We're going to call this onExpiration. Right? And we're just going to package up our timer, and we're going to say, well, we assume we have a timer. Somebody supplies us a timer. Now we see that when was really a pretty bad name for what came out of our timer. What comes out of our timer is the remaining time. So now we've got a better name here just for our variable. So our timer gives us the amount of remaining time. And then we've got our task, and then we've got our scheduler. Okay? So that's the other part of the structure. And now we just have these three dependencies coming into this. And so now we can rewrite our code, and we'll just make those dependencies be arguments. We don't have to assume some global scheduler. If you want to call me with your own scheduler. Execute the code where you want the code to be executed. So now we've got this onExpiration function, and we're going to get the remaining time. And if the timer's expired, if the timer hasn't expired, then we're going to come back and check later, right? So I put the cookies in the oven, I set the timer to be 5 minutes, I walk out of the room. My wife might come in and she might look in the oven and go, those are going to need about 3 more minutes. And so she adds 3 minutes to the timer. I come back after 5 minutes and I'm like, 3 more minutes. So I go and repeat, right? So that's what this is doing. Okay. After the timer is expired, we execute the task. Now, I named this function with a little underscore on the end. I would probably put it into a detail namespace or something if I were writing this code for production, because we can now fix the little issue that we had about the context for the task by basically unrolling one round of our recursion and making sure that we always schedule our onExpiration on the timer. So now our task will always get executed through the scheduler, right? It will just get, it may be that at the time we hit this, the timer's already expired, right? We just want to make sure everything happens consistently. Okay, so by looking at the structure of the function, we can design a better function, right? This is a more general function. It's a more useful function. It has 0 external dependencies, not one. It doesn't rely on std_chrono. It doesn't use std function. It doesn't need some invoke after or some global variable for a last idle. Okay? The only requirements here are the requirements between the arguments themselves, which have a very particular structure. My timer must return a duration that I can pass to my scheduler. Okay? My task must be an object of the type that I can pass to my scheduler. It's a completely self-contained little universe, right? It's really a beautiful little thing, okay? Very general purpose. And if you look, there's not even any heap allocations. I never even called operator new in there, right? And it solves the problem. So let's take a look at another problem. Right? This is the registry problem. A registry is a container supporting the following operations. Right? We can add an object, and when we add an object, we retain a receipt, some kind of token to the thing we put in a registry. We can use the receipt to retrieve the object or remove it. Okay? We can operate on all the objects in the registry, right? So we should be able to just cruise through and say, do something to everything that was registered. Right? So one very common example of this are signal handlers, right? So I have a signal handler, that's a registry. I register a slot, I get back a receipt. I can use that receipt to unregister my slot, okay? When a message gets dispatched, it iterates through everything within my registry to dispatch that message. So that's a registry. So I see this in code a surprising amount of time, right? People usually don't call it a registry, even though it is a registry. They call it a slot or a signal or something else, whatever else they're building. But what do? They use either a map or an unordered map, right? And a lot of people, if they see a map in a code review, they'll say, oh, you should really use an unordered map there. Well, there's actually an important distinction, which is that a map would let us iterate everything in the order that things were put in, okay, which might be important in something like a slot signal handler. That, the first guy to register to receive a message is the first guy who gets the message. And I'm going to pause right there because I said guy. And I say guy a lot at my talks, and that's a bit of a problem. I wish that I could weaken the postconditions on guy to mean everyone. So if I accidentally say guy, do not think that I am excluding anybody in this room. Okay, so we've got this unordered map. We've got this counter that we're going to use for handing out receipts. We can append elements here, okay, into our registry. Maybe append with an unordered map is a bad term, but it started out as a map, and then some guy in a code review said it would be better if I made it an unordered map. So we're appending them. We can erase from the map, and then we can iterate through everything that was in the registry. So it's fairly straightforward. So I get this in a code review, and this is my expression. Okay? Yeah, it's fine, right? So I'm going to introduce you to the Russian code check algorithm. I have no idea if this is how code checks actually work in Russia, but I'm from California, and we don't actually have coats. So, the first thing to realize here is that our receipts are ordered. That's an important relationship. We're handing them out. So we got our pad, we're working the Russian code check here. So somebody comes up, we hand them a receipt, we take the stub, we take their jacket, and we put it on the end of the rack. Just put it right on the end of the rack. Okay? Then somebody comes back with their receipt and they say, I'd like my coat. And you can say, oh, okay, well, that would be about here. Why? Because all the stubs are ordered. Okay, so it's really easy to come along and find the item, right? Right? At some point, your rack is half empty. Every time you pull out a coat off the rack, you don't want to be like, oh, slide those all together. You'll be spending all your time sliding coats together. But at some point, a bunch of the rack is empty, and you're like, okay, now let's just push all the coats down and make room for more coats on the end. Okay? So coats are always ordered by the receipt stubs. And as an additional useful property, coats are always ordered by the order that they were added to our container. So the oldest coat is always at the back, right? And the newest coat is always at the front, right? So I could write a Russian code check here. I have a vector, okay? And it's a vector holding my stubs and an optional value that I want to put in. I'm going to use optional because I want to be able to remove the coat and leave the slot in the rack. Okay? The size here is the number of coats that are actually in the rack, which is a little different than the number of elements in my vector because some of the elements were dead. They got removed. And the ID is the same thing here. This is my notepad that I'm going to use to hand out receipts and stubs. Okay, so now my append looks like this, and now append is magically a better name. I can take my coats and I put them on the back of my vector. And I can increment the size, the count of the number of coats I have. And I returned the receipt there. So this is what it looks like. We've got all the stubs and we've got coats A through H. If I want to erase one, I can use lower bound to go and find the coat, which may not be there, in which case we're just going to bail. Okay? But if we've got it, we'll just mark it dead. We'll just reset the optional value. And we'll decrement the number of coats that we're keeping track of. And then, if the number of coats that we have in the rack is less than half of the number of elements that we have in the vector, the space that we have for coats, only then we're going to come along and we're going to make a pass, right? And we're going to remove all the blank slots and compress everything down so that we have space for the new coats. Okay? Does everybody follow? Pretty straightforward? Lots of nodding. Good. Okay, so what does that look like? So we come along, we mark a bunch of things dead. As people are retrieving their coats, we've got empty slots in the rack. Now we have more than half the empty slots. So we go through and we compress everything down. Okay. Now notice we're still ordered. Our stubs are still 0, 3, 4. Our binary search is still going to work. And we can add additional elements, and everything stays in order, and the code continues to work. Okay, and we can iterate through all the items. We just skip over the dead slots. Right. So if we look at the timing on this, okay, if we come along and we register a bunch of coats into our system here, our unordered map takes this long to add, we're just adding elements at this point, to add a whole bunch of coats. Our vector only takes that long to add a whole bunch of coats. Okay? How long would it take to iterate all of the coats we put in there by comparison? Anybody? About that long. Okay? The gap between these two is about 640. I can iterate through all the coats 640 times, and the delta between the time it took me to add the coats. What didn't I tell you in these statements? How many coats? Does it matter? Did I profile this with 10 coats? With 100 coats? With 1,000,000 coats? It doesn't matter. And here's why. What dominates this graph is the number of allocations I'm making. Okay? So a vector for number of allocations, we know a vector grows linear, but the allocations grow by log n. Okay? An unordered map grows by log n plus n for the number of allocations. So what we're timing with the 640 iterations is the difference in time here, okay, that it takes to add one element. And that grows linearly 1 to 1. So it's 640 if it's 5, if it's 10, if it's in 1,000,000. Now it will eventually start to bend up because eventually the insertion behavior of the vector will move from log n to flat, but really small, right? Maybe it'll get down to 600 out around 4 billion. Okay? That's a lot of times that I could do a linear search, and I'm not even doing a binary search for coats. So, architecture is recognizing that you have relationships that can be exploited for performance. Now, I could probably come along and get the same win here on our coats by using something like a flat hash map of some kind, right? I could get the allocation performance and still have the hashing win, right? I could pull a library to do that. But it's also important that I understand the relationships, which is what Andre was saying, between the relative cost of performance of my operations, right? That's important too. Which finally brings us back to our goal of no contradictions. And so we're going to go back in time a little bit here. Who knows what double entry bookkeeping is? Relatively small number. Okay, so double entry bookkeeping is something that an accountant would know. If you guys were all accountants, you would know this immediately. Double entry bookkeeping is an accounting tool for error detection and fraud prevention. Right? It relies on something known as the accounting equation, which is assets is equal to liabilities plus equity. By ensuring that all transactions are made against two separate accounts, okay, within our system, that's why it's called double entry, right? We have one transaction, we're going to enter it 2 times, and it should be a minimum of 2 separate accounts. The probability of error is significantly reduced, okay? If I do the math twice and then I apply this equation, assets equals liabilities plus equity, and that doesn't hold, then I made a mistake somewhere in my math. Through double-entry bookkeeping, an account gains transparency, making it easier to audit and detect fraud. And in fact, at a lot of banks, you will actually have two separate individuals who are entering each side of the balance to make sure that nobody's cheating and introducing offsetting errors. Right? This is an example of equational reasoning. So this was pioneered in the 11th century by the Jewish banking community. It likely developed independently in Korea in about the same time period. In the 14th century, double-entry bookkeeping was adopted by the Medici Bank. How many people have heard of the Medici family? Way more people than who have heard about double-entry bookkeeping, right? Well, double-entry bookkeeping is credited with establishing the Medici Bank as reliable and trustworthy. They didn't make mistakes. They didn't lose your money. They could tell you where your money came from. This led to the rise of one of the most powerful family dynasties in history. Right? So double-entry bookkeeping was later codified by Luca Pacioli, the father of accounting, in 1494. So the monk here in the foreground is Luca Pacioli. You can see he's probably a Euclid Elements fan. He's got Euclid Solids here, and it's probably Euclid that he's reading in the book there. We don't actually know who the guy is photobombing the picture. He's referred to as just the student, and some people think he might be an artist known as Durar. So every transaction is entered twice, two separate accounts. There are 5 standard accounts. This ensures the mechanical process is done in 2 distinct ways, right? It's not just like I have 100 and I add 10 and I get 110, and I have 100 and I add 10 and I get 110. I'm not doing exactly the same thing twice, okay? And if the accounting equation is not satisfied, then we have a contradiction. There's that word again, right? Our relationship of equality does not hold, but it must hold. Our constraint is violated. Okay. So the next time somebody asks you, well, what's the value of unit testing? You can answer, well, what's the value of the biggest bank in European history? Right? This is why we write unit tests. We're trying to find contradictions. This is why people have the somewhat mistaken notion that software is correct if the software matches the specification. Right? The problem there is if there's a contradiction between the specification and the software, it's actually more likely that it's the specification that's wrong and not the software. Right? What we're saying is that software is correct when the entire ecosystem is consistent. Right? So when 2 relationships imply the same entity has different values, that's what a contradiction is. Relationships are consistent if they imply the entity has the same value, if our accounting equation holds. That means every contradiction has this structure. Okay? We have 2 relationships, and they imply an entity. Okay? This may be consistent. Those 2 relationships may imply exactly the same entity, or it may be a contradiction. Right? So not everything with this structure is a contradiction, but every contradiction has this structure. Every one. This is the structure of a race condition. Okay? This is exactly the structure of a race condition. We have when 2 or more threads access the same object, the same entity, concurrently, and at least one of them is writing, we have a race condition. Okay? If they're both reading, it's consistent. But if one of them is writing, it's a contradiction. Okay? We can solve this by throwing in a mutex. We just add some additional relationship that synchronizes those so that only one value goes through. But what does that mean? Right? Ask somebody in a code review who plops in a relationship into the middle of their code, what did you mean by that? Try to describe the relationship of a mutex. right? Well, it's mutually exclusive. And you're like, well, what do I get out? Well, the last thing that was there when I put it there. Well, what does that mean, right? Is it random? Is it intentionally random, right? You can't reason about a mutex without knowing a whole lot about what's going on in the rest of your system. Maybe it has meaning, but in isolation, all by itself, it's a very difficult thing to think about. Right? So if you have a race condition and you plop in a mutex to solve it, this is going to be my face in the code review. Right? Did you fix the problem? I don't know. Right? You just patched it. You probably just shifted the problem somewhere else. So no raw synchronization primitives. One of the titles from my other talk. We need to get up into something that has higher level meaning that we can reason about. This is why futures and coroutines are an incredibly important concepts, right? So that we can lift up out of here. What about a null pointer dereference? Well, the C++ specification says that dereferencing a null pointer is undefined behavior, right? So we have a piece of code that looks like this, p arrow member, and we get a sig abort, right? That's pretty undefined, right? So what's going on here? Well, the standard says you cannot, the little sideways L is not, you cannot dereference null, right? I had to figure out how to put not dereference null into a circle. And yet we dereference null. So this must be true, it was false, okay? Undefined behavior. That is the link. Well, how do we fix this? Well, we could just throw in a conditional and check. Right? We just write if p, then p arrow. This is the moral equivalent of saying, oh, I've got an assert in my code that says assert, this can't ever happen. So what I'll do is I'll say, well, around my assert, I'll say, well, if it is going to happen, skip the assert. Okay? That's what this is. Right? Now, not always, though. The graceful handling of nothing as a limit is important. Right? We want to make sure that we gracefully handle empty ranges, that we gracefully handle the value 0 as a limit. Right? We have something and we can have nothing. Okay? But we can't just remove sections of arbitrary code to avoid a crash. That is not looking at the structure. That is not architecting our system. That's the novice chess player, right, just whipping his queen into the middle of the board. That's my reaction in the code review. Okay? So a pro tip. Use strong preconditions to move the issue to the caller. Okay? This sounds a little counterintuitive, but you have a piece of code like this, right, which is dereferencing this member, and we already patched it. Do we really have any reason to have a pointer coming in here to begin with, right? Do we need it to be a pointer? Maybe we could just make it a reference, and we could make it the other guy's problem. Right? My dad used to have a saying that was, your fix doesn't have to last forever. It only has to last until the next person's shift. Okay? So what are we doing here? We shouldn't, inside of every function, say, if you hand me meaningless nonsense, that I will somehow try to make lemonade out of that. Okay? What you want to say is, don't hand me meaningless nonsense. Percolate this up and catch the issue outside. So let's look at one more thing. This is a really subtle one. Okay, we have two functions setting the same value through a shared pointer. And I'm using pointer very liberally here. This could be a shared reference even, okay? So what do I mean? Like we have some p and we call set property some value, and somewhere else in the code, we also have p set property. And those p's are referring to the same object. Okay, that's this structure right here. What are the possible meanings of that in your code? Could be that the code is redundant, that they're always setting the same value. Everything's consistent, just one of them is unnecessary. It could mean that they're different sides of the same relationship, right? We might have a relationship on our property, which is our property is equal to some A times B, and we set it in one place when A changes, and we set it in a different place when B changes. Okay? If you're doing that, how long until somebody screws that up and modifies one side of the relationship? Right? You have two separate pieces of code representing one relationship. It could be that they're mutually exclusive, that at any point in time, only the relationship represented by one side or the other holds, right? Right? So never simultaneously, hence never a contradiction. They're separated by time, okay? But that means that there's some controlling entity that determines that is outside of both of those operations, okay? So you have to figure out how to reason about that. It could really mean that what the user intended is just the last one in wins. That is the relationship, right? It was carefully architected to be last one in wins. Probably not. That's a very unusual relationship. It could be some incidental algorithm. What I mean for that is we could be calculating things in some kind of graph, and we're setting this value repeatedly, and we're reading it from other places, and we're resetting it, and eventually we're going to converge on the value that it actually is, right? That's worse than a raw loop, right? We don't want incidental algorithms flowing throughout our code either. It could be that the property isn't really a property, but it really represents some sort of stream or a latch or a trigger. Maybe it's a dirty flag that I'm setting, and everybody's going to set the dirty flag to be true, and then somebody else's responsibility is to read it and clear it, right? Maybe. Or it's just wrong. I'm not saying it's wrong, but it's probably wrong. Right? I really wish that I could have a static analyzer or even a dynamic analyzer that could decorate my objects and say, hey, you are setting this property from two distinct places in your code on the same object. It's probably a bug. I went through Photoshop code base looking for good examples here, and I actually found a couple of bugs going through trying to find places where a property was getting set from multiple places. Now, I didn't bring the examples because the examples were all kind of funky, right? They were doing things like one piece of code was saving away the property, setting the property, clearly the intent, and then running some calculation, and clearly the intent was to restore the property, but they forgot the restore part, okay? So they weren't good examples to show kind of the contradiction structure, but they were good examples just to show that if you're doing this, you're probably not thinking through your code, and there's just random things that are going wrong somewhere, right? Or it could just mean Photoshop's 30 years old, and if you look at it for 15 minutes, you'll find a bug. Yeah, so when I see this, that's my reaction in a code review. So no raw pointers, right? Try not to share data. Keep your reasoning local. Think through your objects. So what does this mean? It means we need to try to learn to play the game, right? We need to learn as developers to consider the essential relationships. And that's really hard. Okay? Because just like everyone in this room is involved in a relationship with everyone else, there is an astronomical number of relationships you're looking at when you're reading a piece of code, right? If you are the novice chess player who's thinking about, well, what if I move this piece here? What if I moved him here? What if I moved him here? And what if when I moved him here, he moved him here, right? You're not playing the game. You have to learn to see at least the board, okay? What is the structure? What is actually going on here? Learn to see that structure formed by all the essential relationships. And then learn to move intentionally, right? Don't just come along and say, hey, this doesn't work, let me throw in a patch, right? I crashed here, patch that, right? You have to think through the implications of that in the rest of your system. You have to look at the structure of your system and say, this is what I want the structure to be, not this is the structure it happens to be. That's architecting the code. Okay? So now you guys are all going to go off and stop talking about rotate and start talking about relationships, right? Well, thank you. So before I take questions, 2 quick slides. If you want to find my talks and papers and ramblings, I tend to post them here. This talk will be up there as soon as I get a chance to finalize it and add a little bit to my website. Me being here is partially sponsored by Adobe allowing me to be here, and I work on the Photoshop team, and Photoshop is hiring, so you can go to photoshopishiring.com, and you can find both the open positions on the Photoshop team, and you can find links to open positions at Adobe in general. Thank you. Questions?
Hi, can you elaborate a bit about why efficiency and safety is at odds and it's provable?
Sure. So let's try to prove this very quickly. I have a vector of items that I want to sort, okay? Or perform any permutation on it. It doesn't even have to be sort. In order to do that, at one point, I need to lift one of those objects out of my vector. At the point that I lift the objects, I have a choice. I can either fill in some kind of meaning into the rest of my structure, but that requires writing data back into that hole. Okay? So, or I can just leave it as a whole. At that point, I have an unsafe operation. This is no longer a valid container. Okay? So I have a very fundamental choice there. Right? I can have full efficiency, right? And we know that doing sort in situ is provably faster than doing, say, a merge sort and always copying, right? So in a functional environment, you're going to say, we need safety at every step. And the cost of that in a functional environment says, well, we're going to do merge sort, and we're going to create a copy, and we can't do quick sort, even though quick sort is provably faster, okay? Or an intrasort, right? So that is where the conflict comes into play.
Does it mean that functional languages are provably less efficient?
Well, most functional languages end up having an escape hatch, right? You have some way in your functional language to say, I'm doing something unsafe now, okay? And I think we need more of that, right? We have too many unsafe operations that are unnecessarily unsafe operations inside of our language.
Okay, thank you.
Yep.
Hi. Excellent talk, by the way, Sean.
Thank you.
I kind of have a question from a point you made earlier about things that exist in C++, 20 in particular, that sort of express relationships. You mentioned contracts, which express relationships between values, and concepts which can express relationships between types and operations on those types. But there's arguably a third, which is C++ modules, which allow library writers to kind of create a formalized relation between entities in their library and the programmer that consumes that library. I was curious as to why this was missing, or am I missing something?
It's a completely valid observation that I agree with, and now I'm going to add it to my slides. So now there's 3, really 2. And it's something that I ignored here and that I think as a community we ignore too much, which is as soon as you are trying to develop software at scale, the relationships between your modules and your build system becomes incredibly important. Okay. So just an omission, not intentional.
Thank you.
Yep. Anybody else? Then you guys get 8 minutes back and you can see me after. Thank you.